Okay, in this session we create the autoencoder MNIST Pi video to understand the autoencoder structure. Okay, firstly we need to import the torch library in here and import torch nn as nn, import torch.optim as optim, and import torch vision dot transform as transform. This is used to build your input dataset. This transform is utilized mainly from this data coming from the dataset in here, like this one, and then this transform is applied to this data in order to build your progression or the appropriate input values to your neural network. Okay. From torch vision import dataset. Okay, it's the pre-trained dataset, and from torch utils data import data loader. This is used for the creating the batch size or the epoch size for your training dataset. Okay. And after that we should import matplot lib.pyplot as plt. Okay, so in the first place we should define the autoencoder structure. Firstly, class autoencoder using the derivation of the nn module. Okay, after that we should give the constructor values of this term, like this one, init, self, and super must be created with the autoencoder and the self parameter in here, and we should call the base class constructor. Okay, after that the self encoder structure can be defined with the nn sequential. Okay, and so we need to give the nn linear neurons for the 28 times 28. These are the picture size 28 and 28, this matrix, but this transformed into the into the linear vector 28 times 28, and so we have this times of 28 times 28 multiplied with one vector should be contained in here. And in the first place we have the 128 data is compressed into this one. Okay, after that nn relu should be given in here because we just create the hard nonlinearity in order to learn the representation of this data. After that we should add the linear neuron in here 128 because the output neuron is the 128, and this is the first time we just get the 128. Okay, after that 64 is given in here, and nn relu should be added in here, and after that nn linear should be added 64 12, and nn relu should be given here, and after that we should give the nn linear 12 to 3. Okay, but this is the compressed representation. And so how many neurons is included in the compressed representation? 3. Okay, so also we should define the self decoder in here, and then sequential should be given in here like this one, and so nn dot linear should be assigned with the what's the first term of this function? 3, and second 12. But we can just take the 12 or the 100 can be assigned in here, but in that case we should utilize these terms. Value, and after that nn linear And what's the first term? 12, 64, and then ReLU, and after that and then linear 64, 1, yes, and then ReLU. And after that, at the final layer, we just have the 128, but the output, yes, 28 times 28. Okay. Do you understand that? Okay. What's the output values of these terms? And then sigmoid function can be created in here because its values are in the range of the what? The 0 to 1, right? As in the grayscale format, we have the normalized image in here. Okay? So, these are the basic code for the what? For the def init function body in here. And after that, we can define another function def forward, right? Self and x can be given in here. X is equal to self encoder x, and x reassigned with what? The decoder x. At the end of this code, we should return to x, right? These are the forward progress. So no, so there's no problem for the different name of these terms. For example, y and z can be used, but it's not useful. It's complicated for your image. Also, if you don't use the self encoder, if you don't use the encoding section, you don't need to define these terms. You just take to define the x and x, right? But the otherwise is current. Okay, there's no syntax error in here. And process the MNIST dataset and transform can be assigned with what? The transforms dot compose the function of these terms, like this one, transforms dot to tensor. And after that, we should give the transforms dot lambda and lambda x, which is given in the what? The torch dot flatten x, because we have the linear neuron in here, not the image. And so at each case, we should flatten the whole data, input data, into this one, R network, right? We have the 28 times 28 matrices or the image in here, but the R encoder and decoder contains only what? The linear vector in the output, in the input, and the linear vector at the output. We should flatten the whole data. And so train dataset can be assigned with what? The dataset dot MNIST, and we just give the root of this term dot data. These are the folders, right? And train is true and download is true, but if this in here, we don't need to download in here, and transform should be applied with the transform. Okay, so train loader can be created with what? The data loader in here, and train dataset, and batch size is 64 and shuffle is true. Okay, and so we set the R parameter with the batch size 64, which means that at each batch we generate what? The 64 images in here, and we take the 64 images and process that, and we get the gradient values of these terms, and after that we update the coefficients of this matrix, these coefficients. Okay? Huh? Yes. Okay, model, loss function and optimizer can be given by the model is equal to the what, the autoencoder, and criterion is equal to the what, and then MSE loss value, and optimizer is equal to what, optim Adam model dot parameters LR is equal to the what, the 1e minus 3. Okay, and so training loop can be created with the what in terms of the for epoch in range 10, which means that we have 10 epochs in here, but for data in train loader, which means that the train loader is generated with the what, the batch size and the shuffled and the train data set, and after that at each section image and stations is equalized to the data. After that image should be converted with the what, the v function can be used to transform this size image size 0 minus 1 is the flatten operation in here, and the output can be assigned with the what, the model parameter and image, and so this is the R generative output in here. And after that loss can be used or criterion by using the what, the output and the image, right? Because the image is the input but also is the R target vector, but the output is the model output, right? And after that optimizer 0 grad should be called to calculate all the gradients in here, and loss backward should be called in here because the error should be split or distributed in a backward way, and we just take the what, the each updated coefficients in here. Okay, and after that the optimizer that step should be called in here, and also we just give the what, to print epoch values of these terms like this one, epoch plus 1 divided by 10, because we have the 10 values in here, and loss can be generated with the what, the loss item dot for f. Okay, these are the basic training phase of this algorithm. Because in this train loader, just using the what, the training dataset, mnist is transformed the whole this lambda function. It's a lambda operation, and torch flatten x can be usable in this form, in this transformation. We just give this feature to it, and after that this transform is updated in the train dataset, and so 28 and 28 can be transformed into what, train dataset features. Okay, we also have the what, the image values 28 and 28, but we can convert now to flatten values. This feature can be usable just now. Let's just see that. Okay, because the size 0 returns this one, and this view generate what, flatten data in here. Okay, because in this case, just see that, visualize the data just now, data iter is equal to the what, iter train loader. Okay, and after that image, next data iter, not in this case this I. Okay, it's the simple term, and with torch no grad, which means that we do not update right now the gradient. At this case we just test in this algorithm, and so image flattened is equal to what the image view image size 0 minus 1, okay, and outputs can be calculated with what the model image flattened, okay. After that we can convert this image into what the 28 and 28 values right now for your reshape image. For your question, just see that the image is equal to what image view image size 0, but with difference of that this 28 and 28. We can convert this image because we can transform this method by using these terms, and so we can enable the whole data in here like this one, okay. And the outputs and outputs, okay. So display data or image in here. Fig and axis can be used with what the PLT subplot plots and rows equal to and calls equals 10 and share x true, share y true, and fig size is equal to 24, okay, and for imps row in zip image outputs and access should be given in here, and for img or img ix in zip chess and row values. After that ax im show values is assigned to what the image squeeze cmap gray, and xget x axis set visible false, and y axis false. After that PLT show must be called in here, okay. So this is just kind of the displaying operation for our algorithm. I'm running this code. In the one epoch we have this termination in here. We're just waiting these values. Okay, we are reaching the end here. It takes too much time for this because I don't have any GPU in here, just CPU. Okay, that's the end. And so just simple as that, okay. So we have give the 28 and 28 matrix into this autoencoder, but we just get the same kind of data, okay. Yes, but for example if I choose this branch, for example 2, but we can set different values of these terms. For example, 32, 32, and 10, and 10, 10, 32, 32, and so if I rerun this code, and so the embedding size is increased to up to 10. Okay, but we just have the 2 epoch in here. In the previous case we have the 10 epoch, but now we have 2 epoch. Just remember that. But at the 2 epoch, maybe we increase the values or the performance of these terms. Okay, just see that. Waiting. At 2 epoch we reach these values. It's more blur, but if we are using, or if we wait until for the 10, maybe it improves the performance of this algorithm. Okay, we just see that. But this is the simple implementation of the what autoencoder structure in the what in generative network.